Welcome to the Rock Raiders, an interdisciplinary team of about 15 students from Rensselaer Polytechnic Institute in Troy, New York. This year, we've worked hard to design and test new systems for our rover. We've incorporated feedback from previous years and grown as a team to create a rover we're excited to show you today.
The project management strategy this year was to have the core rover subteam deliver a rover with base functionality by the end of the fall semester. As this was happening, the mission subteam was focused on designing, researching, and developing the techniques required to do well on the individual missions. Using the fully functioning rover, final implementation of mission-specific tasks takes place during the spring semester. Meanwhile, the core rover subteam will be focusing on testing and gathering feedback to deliver a final design optimized for weight, performance, and efficiency.
The rover's mechanical systems have been redesigned this year with special attention placed on in-house manufacturing. The overwhelming majority of chassis and drive parts can be machined using readily available methods. The rover is built on a four-wheel rocker-type suspension with coupled articulation that aids in traversing difficult terrain. This design offers an excellent balance between manufacturability, performance, and low complexity while meeting URC requirements.
This year, the rover's power systems have seen a complete overhaul. This includes switching our batteries to lithium polymer chemistry for a nearly 50% reduction in battery mass, as well as a new removable enclosure from ProtoCase, which allows for ease of access and repair while we're in the field. The latest addition to the Rock Raiders arsenal is our new base station antenna mount, which can autonomously track the rover's position. In combination with the superior object penetration capabilities of the 900 MHz band, and a high-gain sector antenna, we were able to easily obtain optimal signal strength anywhere within the limits of the competition.
Our autonomous traversal system is in a very strong position. Using a GPS, IMU, and magnetometer, we can already navigate between GPS markers. Thanks to our use of the ROS nav stack, this functionality is quite robust.
The rover localizes itself using the robot localization package. Obstacle avoidance will be done with the Z stereo camera. This has already been modeled in our simulation. It is also capable of visual odometry.
We detect tennis balls with a two-stage approach. We first use HSV color filtering and a Huff circle detector to find candidate tennis balls. We then filter out false positives with a neural network. New this year, we've been doing most of our testing in a simulator of our own design. It lets us very quickly test our algorithms, regardless of the weather outside.
This year's chassis has been designed to handle any challenge the URC throws at us. Critical areas of the chassis have all gone through stress analysis to make sure that we're going to be able to hold up under the forces experienced during extreme navigation. A rocker bogie suspension, 4 independent drive motors, and sturdy aluminum wheels ensure that we're going to be able to handle any terrain. For retrieving items during the extreme retrieval task, we've tested the arm by lifting over twice the maximum weight we're going to be expected to lift at URC. With our arm, our drivetrain, a tracking base station antenna, and onboard GPS, we're confident that the rover is going to be able to lift any item and deliver it anywhere we need.
To complement our 3-axis arm, we have designed an end effector that is placed on a spherical wrist. We use inverse kinematics to calculate joint angles for the arm based on the desired position and orientation of the end effector. This allows for efficient manipulation of the rover's environment. The fingers of the end effector are designed to curl around objects as they close. This allows us to securely grab tools, regardless of their shape or size. The linear actuator operating the end effector has sufficient torque to lift and hold the 3 kg cache.
Our science system has been redesigned in order to accommodate the new parameters of the URC science task. Due to the lack of pure chemicals on Mars, our system utilizes analysis techniques that don't require chemical reactions, such as spectrometers, temperature, gas, and moisture sensors. These 4 sensors give the team a good idea of the general chemical composition of the soil sample. On board, we utilize a microscope alongside a computer vision algorithm the team designed in order to determine the relative eccentricity and size of the soil grains within the soil sample. Smooth and well-rounded soil grains can indicate the past presence of water.
Thank you for your time. Right now, the team's hard at work finishing subsystems and getting our rover competition ready. We hope to see you there.